Welcome to Lab 4 example. We're going to take you through designing the sequence recognizer example, so two input example. So where we left off from our lab videos was this state where we had our state table and we were required to derive the Boolean expression for the flip-flop to represent our present state. So if you look at the state table on the left hand side of this line where my mouse pointer is, this 2x2 is a K-map for your next state. So for your flip-flop inputs, if you remember from the video, you have your stored present state, you have your input, which is your next state, which is based on the input as well as your present state, and then that forces the next state in that is stored in the flip-flop as well as the output of this sequence recognizer. So if you look at the K-map on the left, you can see that there are two instances where D0 should go up to 1. So the two instances are when D0 is 1 and input X is 0, or D0 X bar, or when D0 is 0 and you input a 1, so D0 bar X. Now in the Boolean expression, that would equate to this. So D0 is equals to D0 X bar. So D0 X bar, so it's this one. Or D0 bar X. So D0 bar X, as you can see. Now on the right side of this state table, you have your output. So remember that this sequence recognizer is trying to recognize a sequence of 1 and 0, and only when you press 1 and 0 that it outputs a signal telling you yes, you have entered the correct password. So in this K-map over here, there is only one instance of when output would be 1, and that would be D0 X bar. Now let's translate this into Xilinx. So let's just open a new project. Let's go sequence recognizer, and let me put it somewhere like such. Schematic, yes. Actually, let's change this name into my, not here. Not here. Just keep it in here. There we go. There we go. That's fine. So as mentioned before, the FPGA we're using is a Spartan 6 family, and the device is XC6 SLX4. Yep. So just finish that off. Creates the project. Now we need a new top level. So let's call this sequence recognizer. There we go. Next, and finish. Remember that it has to be of the type schematics. Now let's look at what we need to do. So as you can see, we need a D-type flip-flop to hold our present state. So let's look at our FDC and just put an instance in there. So that's a D-type flip-flop, asynchronous clear, if you remember from counters in Lab 3. And we have an input as well as the present state. So this Q is the present state of this flip-flop. So let me just create a line over there and create a tag. So IO marker, and that will be an output. Now let's change the name of that. So if you double click on that, nets, and just type in D0 and apply, and OK. As you can see, that's changed. So this is your output from your state D0. So D0 would be this present state that comes out of here. Now we also need an input, which is either 1 or 0, which can be represented with 1 bit. So let me just create that. Actually, let me just create it down further out here. There we go, and create another marker, and let's call this input X. There we go, applied, OK. Now, our input into the next state is the sum of products between the current state as well as your input. So let's actually move this to the right a bit. So we can see that it's a sum of product, which means we have two products to sum together. So we will need an OR2 gate. So if you go to symbols, type in OR2, that should show up, and you can put it in there and link it together. Now, the products that we are summing are two input AND gates, right? So D0 X bar can be represented by an AND2 gate, which has an inverted input. Now, Xilinx has already pre-built AND gates, so if you go AND2, so remember that we're looking at an two input AND gate, but if you have more inputs, you can have AND4 gates, you have AND6 gates, you have AND8 gates, and so on. So let's look at AND2 and B1. So B1 means one of the inputs is inverted. One of the inputs is inverted. Just there we go. Yep. And notice we have two of them. So if you go back to our expression, we've got D0 is equals to D0 X bar plus D0 bar X. So we'll have two AND2 gates with an inverted in each one of them. Now let's link the products into the sum, so which is your AND gates into your OR gates, and let's start linking them together. So in the first expression you have D0 X bar, so D0 being your output, so you can loop it back in. So not that. Let's do it. You can link it back together. So it's D0 X bar. So this is the inverted one, so you can put your input X into there. And the second expression is D0 bar X. So if you look over here, D0 is now inverted, so that gets linked together, and X gets linked out there. Now if you double check, that's your output D0, gets fed back into your flip-flop. Now, if you look at the right side, as we mentioned before, that's the K-map for the output, and the expression for the output is D0 X bar. So now we need another AND2B1 to represent this output. So if I do this, put that there, and create a marker. Now the marker, let's name this. So again, double click into there, down in the nets, you have your name. Let's change that to output. In terms of the naming of them, there are two types that you can't use. So in and out can't be used because that is used in the software in the background. So name output is fine. Now let's link it together. So as we said before, the output is D0 X bar. So D0 X bar. You do the same thing. You link D0 and then link X to the inverted input. Now we still have these two, which will be your clock input and reset for your flip-flop, and we can just create an input output marker for them, and maybe just put that as clock in, apply, OK, and put that as a reset button. There we go. Alright, so now this circuit is the full circuit implementation of a two input sequence recognizer. This circuit will recognize the sequence 1, 0, and output will then be 1 when you enter the correct sequence. Now, let's start tools and check your schematics. So that's a good way. So that's no errors or warnings were detected. So it's down here, tools, check schematics. Yep. Since that's giving us no warnings or errors, we can now create the symbol. So go to symbol wizard, using the schematic. And if you have multiple schematics open, you just have to choose the right one that you want to create the symbol for. Click next. Now over here, the order of the pins, it just depends on you and depends on what you're trying to design. For our purpose, there's only 3 inputs and 2 outputs, so it's not going to be too confusing. It only gets confusing if you have, say, more than 12 inputs or more than 12 outputs. That's when you have to start being more methodical and more organized in how you order the pin inputs and outputs. Go. As you can see, once we finish, that's fine. And you can search for that symbol down here. So if you write sequence recognizer, there we go. And that's the symbol that you can input. But for our case, we don't need that. There we go. So that's the 2 input example of the sequence recognizer as per lab 4.